Welcome, everyone. I am absolutely thrilled to have you here today because we are diving straight into something that trips up so many incredibly brilliant physics students. I hear this exact phrase literally all the time. I understand the physics perfectly fine, I just completely mess up the math. Well, today we are going to completely flip that narrative. We are demystifying the math needed for your physics exams. We are going to take it from being this frustrating, scary obstacle and turn it into your most powerful, reliable toolkit. You see, mathematics isn't just something designed to make physics harder. It is simply the foundational language we use to solve complex physical space problems. It's the code that makes the game work. Think of yourself as a game designer trying to level up your exam strategy. Once you truly master this mathematical language, the actual physics concepts, the forces, the energy, the motion, all of it will start to fall into place effortlessly. Your exam answers will level up and you'll be hitting those top marks. So let's get into it. So let me start off by asking you a very direct, crucial question. I want you to really think about your last physics exam, or even just the last practice paper you sat down to do. When you read a problem and you identify the right formula you need to use, do you just plug all the numbers into the physics equations immediately? Do you just start writing down decimals and standard forms the second you see them? Be totally honest with yourself. If you do, trust me, you are not alone. It is a super common instinct. But you are also setting yourself up for one of the most frustrating traps in all of physics. It's a habit that almost guarantees unnecessary arithmetic errors. When the clock is ticking and the pressure is on, plugging numbers in right away is basically asking for trouble. Okay, let's dive into this and compare the two main strategies students use. On the left side of our screen, we have the numbers first approach. This is when you substitute your values immediately. You find the equation and boom, you are instantly writing and rewriting messy, long strings of figures at every single step of your calculation. What happens? Your paper gets cluttered, your brain gets overloaded. It is incredibly prone to arithmetic errors, copying errors, and just simple exhaustion from writing too much. Now, look over to the right. We have the symbols first approach. This is what the top tier students do. It reduces errors significantly, it keeps your workspace incredibly clean, and it mostly relies on writing single, simple letters until the very last possible step. It is night and day, you guys. The difference in your mark potential when you switch from the left column to the right column is staggering. To get you operating completely on that symbols first side, we have structured a very specific, step-by-step roadmap for our explainer today. Think of this as your physics success blueprint. First, we'll start with the golden rule of symbols. Then we'll tackle rearranging equations so you never get stuck algebraically. After that, we'll decode the difference between direct versus inverse proportion. Fourth, we'll dive into mastering physics graphs, which is where so many marks are won or lost. And finally, we will wrap up the whole shebang with the geometry of physics. This is your toolkit. Let's kick things off with Section 1. This is the absolute foundation of everything we're talking about today. The golden rule of symbols. Adopting this exact mindset isn't just a suggestion. It is the ultimate solution to never getting lost halfway through a multi-step physics problem ever again. If you only take one thing away from today's explainer, make it this rule. According to our Cambridge source material, the absolute golden rule is this: work in symbols until you have solved the problem and only then insert the numbers. Let that sink in. Let me give you a practical example. Think about what happens when you substitute a complicated value early on. Let's say the speed of light, 3 times 10 to the power of 8 meters per second. If you plug that in at step 1 of a 5-step calculation, you literally have to write 3 times 10 to the power of 8, 5 separate times as you manipulate the equation. Working purely in symbols, just writing the letter C, saves you precious time. It vastly reduces the chance of you accidentally dropping a 0 or copying down an incorrect figure mid-calculation. Write less, calculate once. It is a completely game-changing strategy. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so you've adopted the golden rule. But to actually follow that rule in the real exam, you must be completely 100% fluent in changing round equations. You have to be able to move the letters around. So let's look at Section 2, rearranging physics equations, changing the subject. Let's break down the two main types of algebraic situations you are going to encounter in your papers. The first scenario you'll see is what we call type 1 equations. These are equations that deal strictly with multiplication and division. Nothing else. The rule here is beautifully, perfectly simple. Whatever you do to one side of the equal sign, you absolutely must do to the other. Imagine an old-school balancing scale. To keep it balanced, any change on the left means an identical change on the right. If you want to change the subject of an equation, like x equals a divided by b, you just multiply or divide both sides by the exact same quantity.
Let's actually walk through this and see how this builds. Suppose we want to make a the brand new subject in that equation we just looked at. We need a to be all by itself. Since a is currently being divided by b, we do the exact opposite. We multiply both sides by b. On the right side, the b in the numerator and the b in the denominator perfectly cancel each other out. Poof, they're gone. And just like that, we have seamlessly isolated a. So our clean final equation reads b times x equals a. Look how clean that is. It's completely simple, and it was entirely done in symbols. No messy numbers anywhere.
Now let's step it up a notch. We have type 2 equations. These are the ones that involve addition and subtraction alongside your multiplication or division. Take a really close look at the example here. X equals a plus b times y. Let's say our goal is to make y the subject of this formula. The big trick here, the core strategy, is that we have to deal with the standalone terms first. Think of it like unwrapping a present. You have to take off the ribbon before you can open the box. We do this by adding or subtracting the same standalone quantity from each side. So let's unpack it step by step. Step 1 is dealing with that standalone a. We subtract a from both sides. That gives us x minus a equals b times y. Okay, awesome. Now we're basically back to a type 1 situation. It's just multiplication. Step 2 is to isolate y by dividing everything on both sides by b. So our final, mathematically perfect equation is y equals x minus a, all divided by b. We successfully reorganized the entire physical relationship, we completely isolated the variable we needed, and we did all of this without touching a single calculator. If you can master this, you are so far ahead of the game. All right, now that we can fluently rearrange literally any formula they throw at us, we need to talk about proportion. Section 3, direct and inverse proportion in physics. Proportion is basically the crucial mathematical operation for finding the relationship between different sets of measurements in an experiment. In simple terms, it answers the question, how does one thing change when I change another thing? This is the beating heart of experimental physics. Let's start with direct proportion. Look closely at this data table. Notice the perfect, predictable one-to-one correspondence here. As our x values increase smoothly, going 1, 2, 3, 4, look at what happens to our y values. They go 2, 4, 6, 8. When x doubles from 1 to 2, y exactly doubles from 2 to 4. When x trebles from 1 to 3, y trebles from 2 to 6. This is the definition of direct proportion. Because they scale perfectly together, the ratio of y to x is always exactly the same. No matter which pair you pick, y divided by x always equals a constant value of 2. We call that the constant of proportionality. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at @Exams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's contrast that direct relationship immediately with inverse proportion. Look at this new table which relates pressure, denoted by P, and volume, denoted by V. As our P values increase from 3 to 6 to 12, so notice that P is doubling, look at what the V values do. They decrease from 4 to 2 to 1. As one variable exactly doubles, the corresponding variable exactly halves. But look even closer at the math here. Their product is always the same. 3 times 4 is 12, 6 times 2 is 12, 12 times 1 is 12. In an inverse proportion, it's not the ratio, but the product of the two variables that gives you your constant of variation. Knowing the difference between these two tables is absolutely essential for your exams. Now, reading a table of numbers like we just did is a great skill, but physics is a highly visual subject. We need to see the trends. And that brings us to Section 4, Mastering Physics Graphs, Visualizing Relations. Graphing is essentially the visual storytelling aspect of physics math. It is used to perfectly and elegantly illustrate the exact proportionality relationships we were just talking about in the data tables. Before you even pick up a pencil to graph, we must absolutely clarify these two fundamental terms that Cambridge examiners love to test. The independent variable is the quantity that you, the experimenter, purposefully and deliberately vary. You are in control of it. This always goes on the horizontal x-axis. The dependent variable is exactly what it sounds like. It's the quantity that depends on the changes you just made. We plot this on the vertical y-axis. For example, imagine you change the current in a circuit to see how the potential difference responds. Because you are controlling the current is independent and sits on the x-axis, and the responding potential difference is dependent, taking its place on the y-axis. When you are faced with a blank grid and asked to draw a graph, I need you to treat this 4-step checklist as absolute law. Do not skip these. 1. Clearly label your axes with both the physical quantities and their specific units. For instance, write capital I/capital A for current in amps. 2. Spread out your scales so they take up the large graph paper provided. Don't squish all your beautiful data into a tiny 2-inch corner. 3. And I literally cannot emphasize this enough. Only use scale multiples of 10, 5, or 2. Do not, under any circumstances, ever use a scale based on multiples of 3 or 7. It is a terrible, terrible idea. It is incredibly difficult to read, your brain will struggle to find the subdivisions, and it almost guarantees plotting errors. Just don't do it. And 4. Mark your specific data points clearly with a small, sharp cross, not a giant, messy blob. So the crucial point is how this visual representation connects right back to the math toolkit we are building. If you plot your experimental data and you get a beautifully straight, continuous line that passes exactly through the origin, meaning the point 0, 0, you have just visually proven direct proportionality. It's right there on the page. But it gets even better. If you mathematically calculate the slope or the gradient of that straight line using your rise over run, that exact number is your constant of proportionality. The math and the picture tell the exact same story. But hold on, what if the relationship is inverse? If you plot pressure P directly against volume V, you aren't going to get a straight line. You will get a curve that sweeps down. Now, curves are incredibly tricky. It's practically impossible to reliably find a constant from a curved line with just a ruler. And this brings us to one of the most brilliant, coolest graphing tricks in all of physics. If you instead calculate and plot P against the reciprocal of V, meaning 1 divided by V, that tricky, hard-to-read curve magically transforms into a perfectly readable straight line that passes right through the origin. It is such an elegant mathematical trick to visually confirm an inverse relationship, and examiners love to see if you know how to do it. All right, we are in the home stretch. We have successfully rearranged complex equations, we've analyzed proportionality, and we've mastered graphing our data. To complete our toolkit, we are moving to Section 5, the geometry of physics, specifically right-angle triangles. So many physics problems, especially those involving the resolution of forces, the refraction of light, or complex projectile motion, happen in physical two-dimensional space. And to decode that space, you absolutely need basic geometry. Consider this your ultimate, indispensable cheat sheet for right-angled triangles. You absolutely need to know Pythagoras' theorem by heart. The square of the longest side, the hypotenuse, which we call c squared, is perfectly equal to the sum of the squares of the other two sides, a squared plus b squared. Furthermore, you must be entirely confident using your trigonometric functions, sine, cosine, and tangent. You need to know how to use them to find unknown interior angles and missing side lengths. Memorize these geometric relationships. They wrap up the complete foundational mathematical language you need to translate physical realities into totally solvable equations. We have covered immense ground today. We unpacked the golden rule of using symbols, manipulating equations without fear, understanding proportionality, drawing perfect graphs, and using essential geometry. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams_IGCSE and click that bell. Don't let another exam pass you by. So I leave you with this final provocative thought. Now that you have the complete mathematical toolkit, will you master the language of symbols before speaking in numbers on your next exam? Try this exact symbols-first rule on your very next practice paper and watch how much cleaner, faster, and more incredibly accurate your physics answers become. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.